So hello everyone and welcome to our workshop. I'm so thrilled to see so many of you here. As I was joking about before, I only saw like 6 forks in our repository and I was thinking that's going to be a small crowd. So I'm so happy to see so many. I'm Elena and we have Chih-Chun as well, and we're from the Cambridge Coding Academy. And today our workshop is going to be focusing on what makes a good model and how can you distinguish it from a one-hit wonder, and what kind of tips and tricks we can teach you in order to make your model better and improve its performance. So just a brief agenda of what we will be covering today. The first session is going to be a little bit of me doing the talking, so it's going to be a little bit of the theory and the background. So we're going to introduce important machine learning techniques such as overfitting and the variance trade-off. And we're going to introduce many different validation techniques, discuss their advantages and disadvantages, and compare them with one another, and see the potential applications. So where would you choose each particular technique to use? Then the second part is more hands-on, more interactive. So you can choose to work independently, but we really like to group people up. We like a lot of the pair programming happiness going on. So if you want to find a pair buddy to work with, that's a lot more fun. You can exchange ideas and work in pairs if you want. And in this session, we will be covering a simplistic model, so K-NN classifiers, and we get to learn how to tune the parameters for this model and visualize the results along the way. And for the third session, we're going to step it up a little bit and cover more advanced models, again, see how we can tune these up and evaluate their performance and compare them with one another. So by the end of the day, we hope that you can be able to determine somehow the goodness of a classification model and comprehend why validation is so crucial when it comes to working with these very powerful black boxes. And I can't stress enough how people tend to avoid and skip completely validation, leading to super optimistic results, which in the end, when it's time to apply to new data, you get very poor quality results, and you're stuck there thinking, what have I done wrong? Last but not least, we're going to see some very good practices in machine learning throughout the whole tutorial. But for our toy data set for the day, we get to work with the publicly available breast cancer data set from the University of California. For those of you that are interested into finding some freely available data sets, this is a very good resource to use. It has a lot of the popular machine learning data sets, such as the IRIS data set, if you want to play around with. And in this particular study, this is a real-world case study, and it contains 569 samples. So 569 patients have provided samples, and it contains measurements of 30 measurements in this case of features such as the radius and the perimeter of a particular sample. Specialized people we specially have categorized these samples into 2 distinct categories, which are benign and malignant samples. And this is, in machine learning, what we call a binary case scenario, because we're working with 2 different independent classes. So once we get to load our data into our IPython notebook, this is somehow how it's going to look like. And it's our job as data scientists to be able to decipher this information and fuse it into our prediction model. Now, once we have our data, it's always a very good practice, and it's always very wise to start by somehow plotting your data and having a look and feel of the background of your data. So for instance, you can choose to see independently one feature at a time by using something like a histogram. So in this case, I can investigate the radius. And we can see that, of course, that for malignant cases, the radius expands over larger and wider ranges than the benign samples, and that's something to be expected. And you can also choose to plot one feature against another. So this is a univariate type of plotting. And this is a good approach because from this plotting, you can see some sort of overlap. So it can give you a good idea of how well can I separate my data. Should I go for a linear model, which is something very simplistic, or should I go for something more advanced, like a nonlinear model? And we can see that in this case, there's quite some overlap. So it can be a first indication of the type of model, the type of complexity we would like to use. Of course, these are only two features, two randomly selected features. You can plot 3 dimensions, or you can see different combination of features at a time, and this will give you a further, more thorough idea. But this is a first step, and it's quite advisable to do so. Now, today we will be focusing with supervised learning techniques, and in particular classification models. And in our classification models, we start by having some prior knowledge. So the idea is like we want to train our model by experience, and in a way simulate the human brain. For us humans, it's very intuitive to distinguish 2 animals from one another, a cat versus a dog. And why is that? Because we've spent our whole lives being trained or being taught how to distinguish the 2 based on certain characteristics, certain measurements, certain features. And this is exactly what we want to feed our algorithm with, this type of knowledge, prior knowledge, in the form of data, in order to use this knowledge in order to predict new unseen data. So we start from our input matrix, which always contains row-wise our samples and column-wise our features. And in supervised learning, we have an associated vector of classes in this case. So we know, for instance, in the scenario we saw before, that certain samples are categorized as malignant and others are categorized as benign. So this is a prior knowledge that we have. And our purpose is to build this prediction model, which is in the form of a mathematical function and nothing else, as a way of predicting new unseen data. So this is exactly the type of approach we would like to see. So a common mistake that people tend to do is train and test this using exactly the same data set. But with prediction modeling how do we determine a good model is by its generalization performance. So by a generalization, we don't mean how well it performs on data we already know and we already have, but from a future unknown data set that may appear at some point in the future. And we need to be able to predict it quite well. Now, this generalization performance, the metric that we will be using mainly today is the overall maximum accuracy. So how many of our samples have been correctly classified, in which case we're talking about the maximum accuracy, or you can choose to use the minimum error if you want to. But at the same time, it's also important to not only focus on the overall accuracy, but also focus on metrics such as the sensitivity and specificity and precision and recall. Because for instance, let us think about Amazon and their fraud detection team. They deal with transactions on a daily basis. They may have millions of transactions happening within one day. And they would like to be able to identify and to spot those transactions that are illegitimate. So those transactions that haven't been made on purpose, but they're actually fraud. And we can think that on a daily basis, this transaction ratio is quite small as opposed to the normal transactions that people do. So if we think that our model is trained based on this knowledge, it may perform extremely well by giving us an overall prediction of 99%. And we can walk away being very happy and think that our model is really good. But does it actually predict the class that we're really interested in? Is our model biased, again, the majority class, and giving us a very good indication about the normal transactions? Is it able to predict this small subset of data that belong in our fraud case or not? So there's this tendency, in order to get this maximum training accuracy, of scientists falling into a very big mistake in machine learning, and that is overfitting. Overfitting is the case whereby we're trying to build a decision boundary, and the decision boundaries, we can think it as the geometric representation of our prediction model. So the idea is we build this boundary and we want our classes to fall on each side of the boundary. And there's this tendency, in order to produce this maximum accuracy, we feed our model with a lot of features at a time. And we tend to make it more and more complicated by increasing the degree in a polynomial or managing and surrounding each one of the samples. And by doing so, by increasing the complexity, we end up with this, let's say, this green line, whereby you can see this zigzag with many creases. Now, In this case, the model will perform amazingly well using the data that we already have. But because it captures noise and because it's so specific and captures independent individual samples at a time, when you throw new data at it, it doesn't know how to predict them. And this is the case of overfitting. So potentially, if we were to use a different kind of decision boundary, such as the black one, it may leave a few of the red samples fall on the other side of the boundary by giving us a slightly lower training accuracy, but it may generalize better. So this is how we determine that a good model is actually fit in this case. The opposite case in this scenario is underfitting. Underfitting is when our model is too simplistic for the type of data we're working with to actually give us a good prediction. So in the case of underfitting, we can think both the prediction error, the training prediction error, and the testing prediction error being equally maximum and quite similar. And this is the case where we notice a lot of high bias and quite a lot of variance. However, as we keep on making our models more and more complex and our boundaries more and more complex, then this is the case where we have a very low training error, as we saw before, because it captures so well our data that when new test data come along, we end up being unable to predict them. So what we're trying to do is find that sweet spot exactly in the middle, this optimum case where we avoid overfitting and underfitting. And the way to do that is by applying validation. So this is probably one of the most crucial things in machine learning, how to select the proper validation for your model. And this is something that is very data dependent as well. So the first and simplest technique to use is the holdout technique, where if we consider that we're starting from this matrix X, we randomly split our data. Let's say we're using a ratio, so 1/3 for our test data and the remaining 2/3 for our training data set. And this will lead us to two independent data sets. So our trained data set and our test data set. By doing so, we leave the test data set completely aside of the whole training process. So it acts as if we have a new data set coming in. And what we're trying to do is train our model and test its generalization performance using our test data set. However, because this split is completely random, completely at chance, we expect it to diverse at a time, so it may lead to high variance. So you can imagine that you may be extremely lucky and have all your best data in your test data set, or you may be extremely unlucky. So this is, again, where you may fall under the illusion that your model's performing extremely well because you have a really good result. However, if you try a different split, will it be as good or not? Another very popular technique in this case that I think most of you should be familiar with is the k-fold cross-validation. And in this case, we split our data into k different subsets. So for instance, if I were to consider 3 different cases, each time I would remove a subset aside and it would act as my test data set, and the remaining subsets will be my training data set. By doing so, we reduce the bias, and depending on how many splits you're going to use, this may often lead to cases of high variance. The beauty with this technique is that all the results from the independent iterations are averaged. So you can have a more robust and a more accurate result out of your validation technique. Special case of k-fold cross-validation is the leave one out cross-validation, where you leave one sample at a time outside. So we can say that each time a single row is left aside. And this is an almost unbiased technique. However, because you leave one sample at a time, and it may be a really good sample to predict or a very low sample to predict, this may lead to cases of high variance. And as you can imagine, this is something that is extremely computationally intense. It takes a lot of time and a lot of resources to do so. And especially for big data set, it's not a very advisable technique to use. Finally, bootstrapping is something that is extremely helpful when it comes to working with really small data. In this case, if we were to start from n number of samples, so for instance, 6 samples, we tend to end up with a training data set that contains the same number of samples. But the idea is that you randomly choose samples out of your original matrix with replacement. So you pseudo-randomize your data in a way. And that's something very popular for those of you who would like to work with random forests. This is something that is extremely useful to know. By doing so, the probability of leaving something aside, so every test data set that is not selected in this replacement process is considered a test data set in this case. And by doing so, we lower both the variance and the bias. So it's kind of an optimized technique to use. It's more robust than the others. However, as you can imagine, it's computationally expensive to do so. Now, the performance of a particular classification model is highly dependent, if not solely dependent, on the parameters of a particular model. And each one of the classification models that we're going to use later today contain a combination of parameters that need to be tuned or tweaked. And the way that we need to tune these parameters, you can go around and provide values one by one and play with your model. But of course, this is not a very nice process. So we need to automate this process. So what we tend to do is combine the validation techniques that we learned now and try to work together towards building a parameter selection. So quite a common technique to do is to use this three-way split, where, again, you leave one test set aside, because this is, again, how you would like to see the performance, the overall performance of your model, the generalized performance. And what you tend to do is internally use another validation technique, either one of the ones we've learned before, and we'll see different cases in our notebook. So you use internally different validation techniques in order to create some pseudo-test cases. And for each combination of parameters that you have fed into your model, you're trying to see its performance. So based on the performance that you get out of it, you select the optimal combination of hyperparameters. So if we were to consider like a k-fold cross-validation in between, for each combination of hyperparameters, you would average the accuracy and end up with the best combination. But don't worry, because we get to see it in practice later on. This is just the theory behind it. Finally, a last type of model, which again is highly connected to the validation techniques we covered, is the ensemble models. And this contains a lot of multiple independently trained pseudo-models, which are fused into a single model. If you like it, a supermodel. So in the case of random forests, this would be several independent trees that create a forest. Or as we were joking sometimes, imagine that you have a lot of different supermodels, like Kate Moss and, I don't know, Naomi Campbell, whichever one you like, and you take characteristics of each and every one of them, all their good characteristics, towards making the ultimate supermodel. So this is the idea. Rather than having, let's say, one very optimistic or one very pessimistic model, you take 100 of them, and by averaging them out, by using some sort of averaging, whether statistical averaging or majority vote, or some type of weighting, such as boosting, you can create this supermodel and make sure that the accuracy, that the performance in this case is far more robust than using just a random model. So it would sum up, in a way, something like this. So you start from your initial matrix, you do this initial split, and internally what we're trying to achieve is optimize these parameters and come up with our optimized decision boundary, our optimized model. And finally, the test set that has been left outside the whole testing process, this is where it comes in. We predict that. If you were to build an ensemble model in this case, you would repeat this procedure 100 times and average out the performance, in this case, the accuracy. So at this point, we'll swap to our IPython notebooks and try to build something in practice. All right, so as a first step, we need to load in our required libraries. So please do let us know if anyone has any issues with any of the libraries. Place your hands up. If you have any questions, please place your hands up again.
Which is the
Yes. Sorry. That's the one. OK, I'll leave the GitHub URL a little bit on. Yeah.
Let's say that I have a long time series data, right? And in my case, doesn't make
long
sense.
By samples or by features or by both?
Long, I mean, 3 years of data, for example.
Okay.
And I know that I can't split it by 2. For example, 2 years and 1 year for testing. It's not going to work. So I thought of it, what would be a good practice, even though I'm not sure because I haven't discussed it with anyone, really having a real opinion. So what I did is I took a moving window, for example. So let's
sliding
say,
window.
2 months of data, and split that period in 60-40 or 70-30. But then I was retraining the model and retesting by moving the window. Yeah. Right. But I had multiple questions to answer. What is the optimal historical training length? Yeah.
Right. So can we get back to that after the tutorial? Because that's very time series specific. So it's like very problem specific. And I don't want to run out of time because a lot of people want to go and drink. But, but we'll get back to that. I'll come right over when I hand it to Chih-Chun and answer your question. So let's just try to cover like what we have here and bring everyone up to speed with that. But I will get back to that one and answer your questions. OK, so anyone had any issues importing the libraries at this point? No? OK, so as a first approach, we're going to try and load our data in. And of course, during a live demo, something is not working for me. Don't you love the pleasures of a live demo? OK, so at this stage, you should have imported your breast cancer data from the provided CSV file. And if we use the head command, you can see some sort of the first background of our data and kind of see what each one of the features contains. So it's only a subset in this case of the first 5 rows. Now, in order to work with the scikit-learn library and any classification techniques provided in Python, we need to convert our data into a NumPy array. And as I mentioned before, it's common practice in machine learning to split our data into our input matrix, in this case represented by X, and the associated class vector, because we want to keep this information independently. So this is where I said before that data scientists need to decipher every time this information. And you need to be able to go through your file and detect where this information is lying and make sure to split the two apart. So it's good practice to also print the dimensionality of your data, because you never know during the import that when something may go wrong and you end up building something crazy, and then afterwards you're just trying to figure out what went wrong in the first place. So at this point, if we plot the dimensionality of our data, we expect to see 569 rows. Everything that's before the comma is representing the rows, and 30 features. And similarly, we expect to see 569 elements in our associated class vector. Now, a good practice is also to have a look at the distribution within each class. So we have loaded our data, but we would like to see how many samples we have in each particular class. And why is that important? Because if we have any sort of imbalances in a majority class that is highly represented over a minority class, then our models later on may be biased to this particular class. So it's something to investigate far in advance, because there may be something that needs to be applied later on, such as weights, as we're going to see. Now, in our current data set, the Y labels are categorical, so they contain both discrete, they can take any of the discrete values. And with scikit-learn, we need to convert them into numeric values. So we fit a label encoder in this case and transform our data into numerical values.
Keep the size of matrix the same, or does
Yes.
it increase as well?
So that is applied on the associated class labels. So that is a vector in this case, and has 5.
Yeah, that's for the targets, not the input, sorry.
No, it's okay. it's not a problem. So yeah, that contains, so if we were to print that before, it would contain values of B and M and have 569 elements. And after we fit the label encoder, it will contain 0 and 1. So we're mapping it into numeric values. Everyone cool so far? Yeah? Cool. So usually, when we're dealing with machine learning, when we're working with machine learning, we don't just take our data and just dump it into a model. It's not as easy as plug and play. Well, I mean, we would have loved that, but it's hardly ever the case. So it's also very good practice to apply some sort of a pre-processing technique. And by pre-processing, it may mean centering or auto-scaling or range scaling or some sort of scaling, maybe log transformations. Unfortunately, there is not a per se command to use in this case, a per se technique. So it's very data dependent. And you have to go in back to your particular problem and see what is more fit. But it's very good practice to apply some sort of scaling. And the reason behind that is if you have some dominant variables that expand over wide ranges versus other variables, it may be the case that your models, again, once more, are biased towards these particular variables. So in this case, what we're going to do is start by auto-scaling our data, because particular models, especially such as SVMs, tend to perform far better when scaling has been applied. So at this point, again, our matrix does not change in dimensions, so we just change the contents of our matrix by centering per column and then applying a scaling factor in each one of the columns, which is the standard deviation. Now, as I mentioned before, good practice at this point is to use some sort of scatter plot and plot one class against another and see how well we can separate the one class against the other. Are my samples overlapping, or are they far apart from one another? And we can see in this case that most probably, I mean, these are just 2 features that we have just randomly selected out of the 30 that we have imported. But in this case, we can see some sort of overlap. So potentially more complex models may be worth to investigate rather than linear models. Finally, the distribution plot. So the histogram, as we said before, we can have a look and feel of the frequency for each particular class. So we can see, again, that the malignant cases are spreading over larger numerical values than the benign ones. Everyone good so far? Any questions? No? Cool. OK, so as our next step, what we're going to do is apply our first validation technique. So good common practice, we never ever take our whole X matrix unless you have for sure a new data set, someone in your lab or someone who is willing to provide you with a new data set. Unless you have someone who can provide you with this type of data, then you're one of the lucky ones. If you don't, it's common practice to split our data into a train data set and a test data set, as we mentioned before. So as a first approach, we're going to apply the holdout method and split our data using, again, like 30% of our data will belong in our test set and 70% of our data will belong in our training set. So if we were to print the dimensions in this case, we can see exactly that. So far, so good?
You want to check if the unbalance is maintained. You talk about like data being unbalanced in one variable.
Yes. So that was me neglecting to cover something. So with a holdout approach, there is a special case, which is called the stratified holdout. And that one. So in this case, instead of just splitting into, let's say, 30% of our samples go into the test case, in which case, as you well spotted, you may end up not having a representative of a particular class because it's selected at random. So you may end up only with samples from one particular class. However, with stratified holdout, what you do is you select 1/3 of the samples, but 1/3 from each particular class. So you make sure that the distribution of your data, as you had it in your initial matrix, is preserved in your test data set. So in this case, this is one of the techniques you can use. You can use a holdout, or you can use a stratified holdout. It's data dependent. You may have like a perfectly balanced data set or not. So it's down to you. We just teach you the tips and tricks, and then you go back to your data and see what works for the best. Yeah? But well spotted. OK, so the first model that we will construct at this point is the k-nearest neighbors. And this is like a very simplistic model. It's the most simplistic out of all the models. And the intuition behind it is that you have a new data set coming in this case, the X data set. And let us assume that we would like to investigate the 6 nearest neighbors, as in this case. So it finds the 6 nearest neighbors using the Euclidean distance. It uses some sort of metric. In this case, it uses the Euclidean distance. So it spots the neighbors that are the closest to the particular sample. And then it takes a majority vote of these 6 cases. So if I had, in this case, 1, 2, 3, 4 red samples and 1 green sample, what do you think my new data set was going to be? Any takers? Any guesses? OK, voting 4 versus 1. I'm sure some of you may bet like for football or something. So I'm sure you know the answer. Come on. No? OK, blue is not taken into consideration, so we're just following the arrows. So we have, OK, let's do that again. Let's try your maths. So you have 4 cases of red and 1 case of green. So what would make our new sample? What would our new sample be in this case? Yay! So well done. Hands up to you. So exactly, this algorithm is very simple because it looks at the nearest neighbors. And rather than building a decision boundary, such as the ones that we're going to see later on in the more advanced models, it just goes to the neighbors and say, OK, so how many female versus male do I have next to me? Or how many green versus red do I have next to me? So this is one way to do that. So we pre-specify, predefine a particular number for the k number of neighbors we would like to investigate. Another one is to use the radius. So we define a particular region, and we see how many neighbors fall into that particular region. So these are the 2 cases. However, one of the peculiarities, something to think about when working with k-nearest neighbors, is that you don't want to take a number such as 2 or 4. So what would happen if I had like 1 red versus 1 green? It's a tie. The algorithm doesn't know how to decide one against another. So in this case, it's good practice to always go with an odd number. OK? So at this point, I'll give you a few minutes to work on the next part of the exercise. And we can all discuss it together. So try and scroll through the k-nearest neighbors example. Don't go too far, though, OK, with the SVMs and stuff. So just try and play around and see what you think. You can work in pairs again if you want to. It's good to discuss with a buddy, with a pair buddy together. So try and play around and see what you get out of the decision boundaries. OK, so we're going to start by playing around with just 2 random k values for our KNN model. For those of you that didn't have the time to finish up, don't worry. You can follow my lead as I speak. So we're going to start by experimenting with 2 random values. So I just chose, for instance, 3 neighbors, which is quite small, and also 100 neighbors, which is quite large. And you can see in this case that our 100 neighbors didn't perform as well as expected. So a good idea would be to visualize these boundaries, so this separation, and see what we end up with. So in this case, when we're working with a very small number of k, so when we're looking into just a small subset of neighbors close to our samples, we can see that, again, we have a lot of patches, a lot of boundaries that surround independent samples, and a lot of creases in our model. It's definitely not linear in this case. And most probably, that may give us an idea that it tends towards some sort of overfitting. On the other side, if we compare and see the decision boundaries created by 100 nearest neighbors when we take a far larger subset of our data, then we see that our boundaries tend towards linearity. So in this case, the slightly lower accuracy that we got may be the case of underfitting, because our model is not as advanced as it should have been, as complex as it should have been, to be able to distinct the data from one another, the categories from one another. And we can see that by using this boundary. Something else to take into consideration, and this brings me back to, again, some sort of weighting you may want to investigate in order to improve the performance of your model. So with k nearest neighbors, another parameter that we can tune, if we want to, is the weights. So before we used uniform weights, which is the default value. And you can also, in this case, investigate weights equals distance, which means that we want the closest neighbors to give more of an input in our model than the ones that are further away. And in this case, if we try and see the accuracy, it doesn't really improve. At least it doesn't improve it for that particular number of neighbors. But this is not the most automated approach we would have hoped for. So rather than trying, of course, independent values, we would like to come up with something more clever, in which way we investigate simultaneously both the different cases, so uniform versus distance, and also the number of nearest neighbors. Again, remember that in this case, we're skipping the even numbers, and we take only the odd numbers into consideration for our models. And we can see that after a particular number, I would say around 50 or so, we see a huge decrease in the performance of our model. So, of course, you can expect at this point that either our boundaries are too complex or they're not complex enough to feed our data so well. So this is something worth investigating. Try different parameters. So that's the whole idea behind machine learning. If you don't choose your parameters correctly, you may end up with something that is either too great or too bad. And you won't be able to know it unless you compare it and have a look on different types of values, different types of parameters. So this is one way that you could go around that. You can choose to graph it in this way by increasing the number of k one at a time and see what you can come up with. However, another approach that is quite common to use for many different models is the tuning with some sort of grid search. So you provide your model with a grid search or a combination of parameters you would like to investigate simultaneously. So for instance, I may want the combination of this number of neighbors and these type of weights. And you throw it into these parameters and the grid search command. So this one here, grid search with cross-validation. And it fixes all the combination for one by one the parameters. So it takes the combination of the parameters together. And the idea is, like, as we said before, what's going on behind the scenes is that it uses some sort of validation. In this case, it's a grid search with cross-validation to investigate which combination of parameters is going to be more fit for our model. So if we were to plot that, we can think of each box as being cross-validated with a particular combination of hyperparameters. So that's the whole idea behind using a heat map in this case. So consider each one of the boxes in our heat map being a completely independent model that has been trained and tested using a particular combination of hyperparameters. So by applying this grid search and using internally cross-validation, it can return to you the optimal combination of hyperparameters. And this is the kind of hyperparameter combination you would later on like to use to finally test your model using the independent test set that we have kept aside. Any questions so far? Maybe some? No? Everyone good? Cool. So in this case, our model didn't actually improve so much. It actually didn't improve at all for the KNN classifier. But maybe a different model can tell us something different. So that can be a good indication to see, can I do better? In every computer science question that we have to answer, any machine learning one, there's always the question, can I do better? Can I speed more? Can it perform better? So grid search is one approach that you can choose to use. But of course, it's quite a computationally intense technique. So with scikit-learn, there's also the randomized search cross-validation, whereby we're just not going exhaustively through one by one the combinations, but it actually randomly picks different hyperparameters. So if you were to plot that, you would see, again, the performance for each one of these parameters. And you can determine the number of parameters that, in this case, the number of neighbors that perform better than others. OK, cool. So at this point, we saw that our KNN classifier performed adequately, but maybe we can do better. So as a next step, we can investigate one of the most powerful, and personally my favorite, machine learning technique. Support vector machines are quite powerful and state-of-the-art machine learning techniques, and they're considered black boxes. And the reason behind that is that their implementation is so complex that we would like to avoid learning more about how it works and just use it as a black box. You feed your data in, and you get some sort of output out. And the majority of the data scientists out there, this is how they use support vector machines. Now, this is really good from one point of view, because it makes our life easier, not doing the trouble and understanding the geometry behind and all the rules behind support vector machines. But when it's time to tune its hyperparameters, especially this technique, is very tricky and very prone to overfitting. So the idea behind support vector machines is that, again, it wants to build a decision boundary that has a low generalization error or a maximum generalization accuracy. But the whole idea is that it's different because we're trying to maximize the distance, also called as margin, between the nearest points of the two classes. These nearest points of the two classes are what is called support vectors. And the difference of support vector machines versus any other machine learning technique that constructs a boundary is that it does not take all the samples at once to find the distance towards this boundary and find how to maximize this margin, but it only takes the nearest points between the classes. So we can imagine that we can split this region using as many planes, as many lines as possible. But we're trying to find the optimal line, or the optimal hyperplane, that accurately separates these two regions by using only this subset of samples that are closely found to one another. These are the ones that are termed support vectors. Now, to begin with, support vector machines did not allow any misclassifications. There were hard margin SVMs. But one of the parameters that was later introduced, one of the hyperparameters in SVMs, is the cost or the penalty factor, whereby we allow some training misclassifications as a way of increasing our generalization performance. In this case, as our cost increases, then the misclassifications become more and more significant, and it may, and most probably will, lead to overfitting. Now, what happens in the case where our input space is far too complex to fit a straight line and accurately separate the two classes? In this case, we will need to step up towards a nonlinear classification and a nonlinear boundary. But how do we do that? this is where the most powerful attribute of support vector machines kicks in. And this is the kernel trick. So we start from a non-separable input space. And then we have a very cool, powerful kernel function doing everything for us. And it projects the data into a higher dimensional space. This space can be possibly infinite dimensional. And this is where overfitting may be also, it may be a case that overfitting may actually happen. And in this feature space, we're trying to find, again, an optimal linear, hyperplane that tries to separate the two classes from one another. So we can see in this case that if we project into a three-dimensional space, there's a hyperplane that smoothly cuts in between the two cases, whereas in the input space, that's impossible to do so. And by back projecting this optimal linear hyperplane into our original space, this is when we end up with a non-linear boundary. So ideally, we end up with something that looks like this. Now, the RBF SVMs are the most popular out of all the kernels, out of all the off-the-shelf kernels that support vector machines provide to us. And in this case, in addition to the cost parameter, which is common across all SVMs, there's also the gamma parameter. And this parameter determines the degree of nonlinearity of our models. So we can see that by going too low with the gamma parameter, we have linear boundaries, which may prove to be underfitting our data. And by going too far, as gamma increases, then the decision boundaries become more and more nonlinear. We have a lot of sharp peaks, a lot of individually surrounded samples, and some spiky functions. So again, this is a case of overfitting our data. And SVMs are one of the most powerful techniques, but again, I can't stress enough that if you don't apply proper validation, you may end up with an overfit in your data. So once more, one of the most common ways to tune our support vector machines is to use some sort of grid search, including validation. So again, we can consider a combination of hyperparameters of cost and gamma. We usually go exponentially and check these parameters. And yeah, we can consider that each one of these boxes contains some sort of validation. So for instance, you can have internally k-fold cross-validation or bootstrapping in every one of these boxes. And this will give you a good indication of where we can find a good parameter region. So what combination of hyperparameters are going to make our model more robust and give us the best generalization performance. If you choose to do that, you can also follow it with an extensive grid search, so a finer tuning within that particular region of good parameters. If not, and grid search is a perfectly simple, very simplistic approach to follow, but it is very time consuming. So sometimes using a heuristic can be an alternative. But it's always a first step to try with something simple like grid search and see what that gives you before moving to more complex and heuristic approaches. So at this point, let's go back to our IPython notebook and play around with SVMs. So I'll give you like 10 minutes to take your time and play around with SVM so we can discuss the results. OK, so how is everyone doing? Good? OK, so as we said before, we can start by investigating linear SVMs, because it's always good practice to start from a simple linear model, even if you know that your data is most probably likely to be nonlinear. It's always good practice to start with a simplistic linear model and work your way towards something more complex. Because if you attack a complex model all in one go, you may come across different situations, such as the imbalance or the cross-validation or any other thing that you may want to investigate using a far simpler model before you also throw in the kind of tuning of the hyperparameters of a particular complex model. So if we start in this case by using our linear SVMs, and in particular use the default values given to us for the cost function. So remember, our linear SVMs are dependent on the cost parameter in this case. So again, we train our data using our trained data set, and we test it with our independent test data set. And we can get a fairly good result out of SVM. So we can say that SVMs performed far better than our KNN model. But can we do better? Again, the question that we keep asking ourselves, since we got a hint of nonlinearity before in our data, can we do better? Is a nonlinear model going to give me a better performance than a linear one? So if I were to investigate at this point a nonlinear model and use the default values, we can see that it actually performs quite well. It performs equally well as a linear model. But in this case, we're taking into consideration our default parameters. And this is one of the biggest mistakes. You wouldn't necessarily take the default parameters of our model. You would experiment with the hyperparameters and see how far you could go to have a better model, but without overfitting. Once more, in order to achieve that, we would like to investigate our grid search tuning. So we would like to have grid search performed with cross-validation for a predefined range of hyperparameters. So I predefine the range that I would like my hyperparameters to take. And these are the hyperparameters that I will feed into the pseudo models I'm creating in each grid search iteration. So again, you can choose to plot these results by using a heat map and get an indication of a good parameter region. So we can see that in this region, our model most probably has our pseudo models returned back to us and reported that these are very good regions, so very good combinations of hyperparameters. Now, once I retrieve the best hyperparameters, the best parameter for cost and the best parameter for gamma out of my cross-validated models, we can see that once we apply these parameters to our models, no surprise, we get a 99% of our data being correctly classified. So you can see, of course, in this case, our models perform to begin with quite well. So we started from a 96, moved to a 98. But we can see that there is some improvement by applying some tuned parameters in our model. Just something to bear in mind in the case in particular of SVMs and grid search validation is that when you do this grid search, first of all, it's a very simplistic, easy to understand approach, very intuitive, but it's quite exhaustive and time consuming. And it takes a lot of combinations and a lot of time, computational time. And something else to take into consideration is that we're looking into a particular region. And within this region, you may have one tiny peak that may be the best parameters possible for our model. But with a grid search, unfortunately, you can't tune it down so thoroughly. So possibly a heuristic, another implementation in this case, some sort of an optimization algorithm could be more fit. But again, I would say always start by using simplistic techniques such as cross-validation and grid search before you move on to something far more advanced. So if you have any questions about other types of heuristics and things you could use, I'm more than happy afterwards to answer all your questions. For now, I'll pass you on to Chih-Chun, and she's going to talk you through logistic regression and some neural nets.
Yep, this is just going to be a really quick one, but it's just so we cover like some breadth as well. So basically, I mean, the intuition behind logistic regression is very similar to linear regression. So you can see it really as an extension of linear regression. What you're actually outputting is a probability, though. So you're outputting a value between 0 and 1, and then you're using that to make some sort of decision. So you can see, just as in linear regression, you have coefficients before each of the terms, you have weights or parameters before each of the terms, which are your features with logistic regression. And then you combine them using some sort of function that adds them, aggregates them, usually adding them. And then you have another function that determines how you make the decision. So sometimes it's an absolute threshold. Sometimes it's like you use the outcome that's the most likely out of the whole range of outcomes. And that's what you use to basically base your prediction on. So that's the intuition behind logistic regression. The important thing about that is that basically it's still based on a linear function. It's basically an extension of linear regression. So that also means that the decision boundary is also linear. So as you can see from here, the separation between the two classes is a sharp line. And in terms of hyperparameters, so the main ones that get tuned are the penalty function. So what you're using to basically determine how much something's deviating. So the two penalty functions are least squares and absolute deviation. So that's a hyperparameter that often gets tested. So absolute deviation is like the absolute value with which it deviates from the prediction, whereas least squares is taking the square of the values. So just very quickly on neural nets. So yeah, you can see it both ways. So on the other hand, you can see logistic regression as really just a simple one-layer neural net. And when you link them, you basically get a multi-layer neural network. So the thing with the neural network is that you have this hidden layer, one or more hidden layers. And that's the part that gives you the non-linearity. So if you just had a single layer, it would be just like logistic regression. But it's the non-linearity you can see is lying in here. But unfortunately, just like with SVMs, that's also what makes it a tricky model to understand and to tune. So actually, that is an issue with neural nets. So there are actually, even if you were just going to do hyperparameter search just by looking at the architecture of the neural net, that already, if you think about how you can explore that architecture, that's already a huge parameter space. And that's why it's a very, if you think in terms of the optimization and the reliability, if you like, of neural nets, that's kind of one criticism that they've received, even though they're really hot at the moment. Also because of the non-linearity, they're highly general, and they can fit very complex models. So this is something to bear in mind. You have to trade off like this sort of black boxishness, which some people may be more or less comfortable with the complexity of the model. So as you can see, like here, for example, this is like a lot more non-linear decision surface, and it can get a lot more. I mean, I'll show you in a minute with the IPython notebook. You could get some very intricate, decision boundaries. So again, overfitting is a big problem. So now if we switch to the IPython notebook now. Oh, I may need your, because it's a laptop. Is it Chrome? So if I leave you some time to play as well, I think, it's 10 minutes away, so we'll allow 5 minutes and I can talk you through it. How's everyone doing? It's okay, I'll just run through this very quickly then so we can go and have a drink. So basically, again, if we use the default values for logistic regression, which is built into scikit-learn, we get pretty good accuracy. I have to say, working with this data set was frustrating because it was actually quite an easy data set. So as you can see, our accuracy scores are pretty high, but we always want to do better. So this is with the default values, you get 0.98 accuracy with this linear decision plot. And just to have a look at the default values, you can see that in scikit-learn, the penalization is L2. And then the cost is, this is the regularization rate, so something that Elena talked about as well. That's another hyperparameter that you can tune in logistic regression. So you get that with the default values. And then doing a grid search over these ranges, you end up with, so the cost of 0.5 and penalty L2 gives you the best results. Which is 0.99 accuracy, again improving. So just to see that on the plot again. So you'll see this is quite interesting as well, because you saw before with Elena's plot, some of the, with the heat map, the best performances were together. But here it seems that you've got kind of hot regions in different areas. So that's an interesting feature as well to look out for. And then with neural networks again, so these values give you 0.97. And then if you play around, again, if you look at this decision plot, very strange shapes emerging here, depending on what you feed in. Like this one with a 3-layer architecture gives you this. Brilliant. Again, doing the grid search over these ranges, can explore that, end up with this. Again, it's interesting, the shape of the heat map as well. So yeah, that's kind of ends our session because I got away before. And if you have any more questions, just feel free to ask. And I just want to show you our last slide because Elena,
Took me a while to find it.
she was,
I put a lot of effort.
yeah. It's a parting thought, I think. There we go.
So never ever trust your models. Make sure that they're accurate. That's the bottom story. So a few things to just wrap up. First of all, you need to give a high five to your pair buddy, to your programming buddy, because you did so amazingly well. And I don't want to keep you away from drinks. I know what Pythonistas can do for a drink. And just a few things. For those of you who have asked about access to all the code, it's going to be there. We won't remove it. It's on the Cambridge Coding GitHub page. You can either copy the link at the moment, or you can find it through the abstract of our talk online through the PyData. I'll just leave it a little bit for you to play around with. Keep in mind, have a look in our Cambridge Coding website as well, because there's a lot of exciting workshops coming up in Python. So for instance, a lot of regression workshops and neural net specific workshops on supervised learning technique and others. Or we can tune down and have a private session depending on your needs if you want to. And last but not least, if you want to come and grab us for questions or anything machine learning related, or if you want to subscribe to our mailing list, please let us know. And there's some flyers as well. Chih-Chun has some flyers over there. But thank you all so much. Thank you.